Okay, so yeah, hello everyone. Uh, we are continuing our sections. So the 3.1 about introductions, about the some theory of existence of higher order differential equations, and also I think the most important thing is the last part here, which is this part. So what you need to remember for the higher order derivatives, we are going to have a structure that our solution should include, we call the complementary solution, complementary solution, and the particular solution. The complementary one we could get from the homogeneous equations, and the particular is particularly on that equation. Okay, so this will be the general solution for non-homogeneous. I think it will be better if we going through some techniques to see what kind of answers or what kind of solutions we are going to have. Okay, so today I would like to start with one techniques that it is called the reduction of order. Okay, so by name, reduction of order. So it's supposed to be reduce something, so reduce the order. So if it's higher, then our goal in this technique is to reduce the order until it's become the first derivative and use first derivative techniques. In our case, mostly this will be completed by linear differential equation at the end. But let me just tell you how we are going to approach this techniques. Okay. I think I was just taking this off. Okay. Let's say we have, suppose we have y of x is a solution. Okay, now we have second order, right? Second order differential equation. As we remember from the theory, from the introduction, we should get at least y1 and y2, right? And we know that y1 and y2 cannot be linear independent. They should be independent, right? So that they have specific or particular solution. So we need to find, okay, so we need to find, so we need to find y2 so that y1 and y2 linearly independent. Okay, that's the first thing that you need to keep in mind. So because y1 and y2 is they both linearly independent, so they don't have any ratio in scalar, right? So if I write y2 over y1, this will equal non-constant. Okay, this is the first rule. Okay, that y1 and y2 we should make them as non-constant. The ratio is non-constant. If it is constant, then it's linear dependent, like we did, I think, on Tuesday class, right? Okay. So if not a constant, then perhaps this is another function. Okay, so that's how we are going to use that. So that we can take that as, let's say, another functions of, let's say, ux. Okay, so we could have that y2 or y2 of x is equal u of x and then y1 of x. Okay, so it's like a substitution method. Okay, it's like substitution method. So we are going to sub y2 of x into differential equations. Okay. And our goal actually, we need to find this ux. We need to find this ux. And then at the end, because of that ux, we can find and determine this y1 and y2 at the end. I will give you some practical example and then give you the formal definitions. Okay? So you can have more practical approach and understand from example. So let's say we are given our y1 is e with power of x. Okay, it's a solution of differential equations y double prime minus y equals 0 on all x or all on interval from negative infinity to positive infinity. The question is to find what is y2. Okay, I think one typical problem for this method is usually we are given y1 and we need to consider the differential equation and then find y2. So we are going to try and take the y2 using this ux. So we multiply y1 with ux. We put here, and we are going to derive at least twice to compensate this equation. And we substitute here. So now let's try. So take times, let y2 equal ux, and then multiply with, let's say, y1, and this is equal to ux equal to e with power of x. Okay. So y2 prime is u. Let me just write u without the x to make it easy. So u e x, okay, plus u prime ex, right? And then one more time to take the second derivative. U ex, this is again it's the same, and this will be equal to u prime e with power x, and then plus u double prime ex, right? Just a normal product rule. Okay, from this part, we are going to substitute to our differential equations. Okay, so we are going to move this double prime back here, and then this y over here. Okay, so we are going to have this minus with this. Okay, we are going to see that this will be canceling out, right? Oh, let me write completely. So we are going to have
u, or maybe just copy this long equation and put here, and minus y is ux e power x is equal to 0. So we are going to have cancellation. Maybe this is to make it the same. Okay. Okay. So we have that as our equations, and we can write ex. Let's write ex. And this will be 2u prime ex plus u double prime ex equals 0. And ex is, we can factorize. This will be 2u prime plus u double prime and equal to 0. And from these equations, we know that the e with power of x is always positive. So the one that we can make this equation 0 is the inside. So let's observe this 3 prime plus u double prime. Okay. So we can sure that the e to the x is always positive, or we could also say e to the x is never going to be 0, right? So we are going to write that the 2u prime plus u double prime. Oh, let me write u double prime first to make it more clear. To u double prime plus 2u prime is equal 0. Okay, now it's the deal. So we have double prime and prime, okay? So the idea is to make this order reduce. We need to make this order to be reduced. So let's consider a new substitutions. Okay, so let something equal to u prime, maybe w. Okay, maybe w. Let's say this is equal to u prime. Okay, so if I have w prime, this will be u double prime. So if we exchange this, we are going to get, this is y prime, w prime, and plus 2w and equal to 0. And this is actually, we can use separately. You can also use the linear differential equation. I'm going to take linear differential equation to refresh our techniques. Okay. So let's say we have, if you remember, the differentials is having this, right? So we take the integrating factor of 2, right? 2dx, let's say 2dx, and this will be e with power 2x. So we multiply e to x w prime plus e to x 2w equal to 0. And we are going to have our product form, which is e with power of 2x w. Okay, right? And then it's equal to 0. And then take the integrations. Take the integrations. Let me write here. Okay. So e to x w. This will be equal to a constant. Okay. Let's say it's c1. Okay. And w is c1 multiplied with e negative 2x. And remember that this is still in w.
we are going to get back to our original equation, which is u prime. So u prime is c1 e equal to x. And then we need to get to u. So we integrate one. Okay, let me write this continuation in the next page. So you can write this first, and I will continue in the next page. It's not very simple, and usually when we reduce, the final form or the final techniques is using it usually linear differential equation. Well, if this is 0, I think you can use this reciprocal. But mostly we have another component here, and perhaps linear differential equation is, I think, the best choice for this one. It always work for the second order. It always work. You have higher than 2. I think you need to give different mapping.
Okay, let me continue on the next page. So since W is u prime, okay, then u prime is based on what we have, c1 e negative 2x. So we are going to once more integrate with respect to dx. So we are going to have u, and we have half, okay, because it's e power something. And it's negative half, sorry, it's negative 2x. So negative 1 over 2 e, or c1 e negative 2x plus another constant. So u, okay, u is, we get y, or y2 is ux e to the x, right? So we multiply this u with e to the x. Okay? So we are going to have another form. So this will be negative c1 over 2, and then e plus x, so minus 2 plus 1 is minus 1, right? So minus x, and then plus c2 e to the x. Now what's next? What's next? The next thing is we need to propose our solution. What kind of solution that we can assume? Okay. First is the constant can be any constant. Okay. So my suggestion is to leave one because e to the x is already given as y1. So we are just concentrating on the other side. So we need to make this part. Let's just make it disappear. So let's say c2 is equal to 0. Let's say assume. Okay. So we choose. So choosing c2 is 0 and c1. Let's make it clear that it's 1. So let's make c1 is just 2 or negative 2. To make it disappear. So we are going to get the proposed solution is y2 e with power of negative x. Okay. But we are not done really yet, because the next thing is you need to also prove that this is the correct solution. How to prove that? We are going back to the linearly dependent, the Wronskian, and make sure that this is going to be linearly independent with the given y1. Okay. So check whether y2 propose y2 is linearly independent with y1. Okay. So we can write using the Wronskian. So we can decide to take the Wronskian. I think this is not too complicated. So we are going to cross multiply this and minus with the other one. So we are going to have 1, right? Minus 1, right? So this will be 2. So it's not, so we say that the Wronskian is not equal 0, which means that y2 is linearly or y2 and y1 or are linearly independent. So at the end, y1 is e to the x and y2 is e with power negative x. So don't forget to write the general solution. So general solution of y double prime minus y equals 0 is y equal negative c1 over 2. We get back to this particular formulations. And then e negative x plus c2 e to the power of x. So that's how it works. Okay? So we basically, technically, the typical question is you will always given y1, and you need to predict or make some suggestion for y2, and you need to prove it, and you need to arrange the general solution. And of course, I think the way you did all this, the procedure, it is like this. But of course, we have the official procedure and proving. We'll get into that after the tape. Basically the same thing, but using this symbols. Okay, now let me give you the general case, okay, the general formulations. So general case, So suppose the standard form okay, let's say this is the standard form. Okay, P and Q can be any function of x. Okay, and of course we need to assume that all the functions should be continuous. So P of x and Q of x are continuous on some interval I. If not continuous, then it doesn't work, right? We already learned about the existence and uniqueness. That is actually about continuity. And that's the first question on your quiz also. Okay, so let y1 x is a solution or is a known solution on interval I, and y1 also not equal to 0 for every x in interval I. So if y, let me write y2 in terms just y, okay, to make calculation easily, because if I write y2 is become messy. So let me write y is equal to ux multiplied with y1, okay. Then we can derive this. Derive becomes y prime u y1 prime plus u prime y1. Okay, and then take one more time. So u y1 double prime plus, and we will have plus 2 combination like we did before, right? So we are going to have this and y1 u double prime. Okay. Now let's put all this together, y double prime, y prime, and y, into our general solution or general equation, the differential equation. So subs y double prime, y prime, y equations into differential equation. Okay. It's become y double prime, we could write I think I will write the conclusions. Okay. You can write if you want steps by steps, but let me write this y double prime plus py prime plus qy equal to u y1 double prime plus p y1 prime plus q y1, okay, and then plus y1 u double prime plus 2y1 prime plus py1 and then u prime, and this is all equal to 0. And practically we take the y double prime is this, right? And we are going to write here, and we combine some parts and factorize u, and then the same thing, and we are going to have all factorization of u, so u prime, and you have u double prime. So basically just substitute inside and arrange the order. Now this part here is the same thing as the general equations that equal to 0. So this is equal to 0. So we are going to write that this will be y1 u double prime plus 2y1 prime plus py1 and u prime and equal to 0. Okay, now this is the thing that we need to reduce. So after substituting with u, the one that we want to reduce is this u. We have the second order here. We are going to reduce this and becoming, reduce 1 to make it linear, to make it linear first order. Okay, so you can use W or phi. I will use W. Okay, use W. So then when we have W prime, this will be U double prime. So we arrange these substitutions, reducing the order in the expression. Okay, now we can substitute. So y1 w prime plus and then u prime becomes w. And then we can arrange this into our linear differential equation. So we can define with y1. So define with y1. So we are going to have this is the w dx, right? Divide with y1, so plus w over y1 and then 2y1 prime plus py1. Now perhaps we can also write perhaps you can also take separate these equations. I think I will continue the next page. I don't have page more here. I'll maybe finish off this multiplications. So 2w y1 prime over y1 plus pw equal to 0. Okay, let me copy this. Okay, let me wait for a moment. You can take notes first. What I want to write is actually what kind of like direct formulations we could have. We have like in this general case. But if you don't mind to memorize that, I think doing the first practical approach, that's also fine. Doing directly, as long as you know what is your goal, finding the y2. Okay. Now, we could separate this, I think. Let's divide with y. Multiply with 1 over y. So we will have, and multiply with also dx. So the first component will be dw over w plus 2 y prime 1 y1 and then dx and then plus p dx. Okay, or maybe let me write p dx, move to the right side and making this negative p dx like that. And take the integrations, so all will be integrated carefully. So we are going to have ln plus ln, this will be y1 squared, okay, y1 squared. You can check. If we differentiate y1 will be 1 over y1, and then this will be general to y1 prime, right? The implicit, okay. And then equal to negative p dx. Okay, so let's just keep this p dx as integral defined function. Now we could take this ln and make it combining these two. Okay, like that. And then we take the wy1 outside of the ln, and we are going to introduce e, and this will be power with negative p dx. Oh, I forgot the constant. The constant, let me add the constant here. Okay, I forgot this one. And since it's e, so e with power of c, so I will take another c as multiply with e. So let's say c1 here. Okay, since it's w, then let's go revert this w, revert back to the u prime. Okay. And u prime is equal c1e and then over y1 squared. And then we need to get back to u, so we are going to integrate once more. And we are going to have u, c1 integrations, e over y1 squared. Let me make clear. Dx and then plus another constant c, c2. And we can let c1 just 1 and c2 is, let's say, 0. So we are going to have, let me write, remember that y is ux multiply with y1 x. So y2 is y1 of x multiply with all this. Or maybe with x like that, square dx. Yeah, this is some kind of direct formulations. Okay? So I think not easy to be remembered.
cheat sheet, maybe this will be helpful. Okay, and also, for all integrations, you can confirm with your calculator, okay? At least to confirm whether your process is okay.
Maybe we can have some example to use this y2. So let y1 equal x squared is a solution of x squared y double prime minus 3xy prime plus 4y equals 0. Okay. Find general solution on interval from 0 to infinity. Okay. And usually if the case is just finding the solution, usually the question is already like in a good and correct way of writing. It doesn't mean you need to like check the existence or not. It's supposed to be exist. But unless the question is asking about that. So I think you can make that assumption. You can make this assumption. Okay, I think you can try this method, A1, 2, and then put y1 here, put p. So maybe the first thing is to maybe clean this structure using the standard form, and make out the p. Okay, make out the p, which one is p, and then you can put here, put this in this equation. But again, whenever you maybe not really confident or maybe not really, maybe sometimes the form maybe not good, then perhaps going for using the u, y2 is u multiply y1, maybe that's also okay. But that will be a little bit longer. So if we put y1, okay, y1 is x squared, and then we find p from that structure. So we write the standard form. That is, we need to divide with x squared, right? So y double prime minus 3 over x y prime plus 4 over x squared y. So this will be p, right? This will be p. So we are going to have y2 is x squared integral e integral, this will be minus, so minus is plus, so 3 over x dx, and then x squared and then squared become x with power of 4. This will be x squared. This will be 3 ln x, and this will be ln x cubed, and e with power of ln x cubed becomes x cubed, so we can have x cubed over x power 4 dx. So we are going to have integral of 1 over x, which is the ln x. So since the interval is from the positive one, we can just make it ln x. Okay, no need to take absolute value. So we could take this x squared ln x. So how to write the general solutions? We could write the general solutions y c1 x squared plus c2 x squared ln x. So this will be the general solutions. Okay. I think because of this formulations, we could finish this problem, I think, quite simple and short. And I think that's the reduction of order. We could have more examples, but I think I will hold that and give you later after we have more techniques, and we can review after that. Maybe next week, I'm giving you another techniques and then maybe homework. I think that's it for today. We are not having any feedback, but we are going to have your result. Okay, I will deliver your result. Okay, maybe. I think if you get around 50 something, 60, still okay for me. Okay. Yeah, sorry. If you get lower than that, it will be Why number one? Please, George. Kenzie and Harriet. The average is actually around 50.